Hello everyone, and this is our lecture number 12 of this video lecture series, Antenna and Wave Propagation. And since our classroom sessions and online this video lecture session, we have been studied various antenna configurations and like linear antennas or slot antennas or reflector antennas, aperture antennas, and all. We have studied many special antennas like low periodic and Yagi-Uda antennas also. Today we are starting another uh, very important portion of the subject antenna and wave propagation, that is propagation of radio waves. Since our first class or from our last complete sessions, we had studied various antennas and we consider the environment or the surrounding of the antenna as infinite free space. Okay, we consider that the antenna is situated at some particular points, the origin of the coordinate system, and it is radiating into free space. And then we find the field radiated by the antenna in the free space. But actually, when we deal with practical environment, this is not so. I mean, this finite free space is not always available. And in general, we have antenna in a bounded medium. There are many limitations by the surrounding imposed on this performance of antenna. And that's why the radiation characteristic of the antenna will not be exactly as we have seen till now. That will be the practical results related to the fields radiated by the antenna will be combination of both the theory we had studied till now and the distribution, or I should say the surrounding, the enclosing the antenna. So that's why this topic is very important to study, that how waves propagate in different environments, the different practical environment. Though though we are saying, or I am saying that it is the study of the practical environment, but when we go on studying all different kinds of propagation of radio waves, we have to consider some specific situations. We cannot make it perfectly practical. We cannot include all the effects, which all the objects which affect the performance of radio wave propagation. But these models, what we will go through, are, I mean, they are more appropriate. Or applying these models to practical situations will produce the same result all in all as the actual experiment will give you. Okay, so we will have to, or we will study various propagation modes of radio waves. And as I told you that there are many effects from the surrounding. The three major effects of the surrounding on the propagation of radio wave is the first factor which affects it is the spherical shape of Earth. As we had studied till now that you have a transmitter placed at some point P, placed at origin, and point P is the point of observation where you need to find the radiated field due to this antenna. And we consider that the distance between these two is very, very large as compared to the wavelength. And we are free to assume this distance to be infinite also. Okay, but in practical situation, the transmitting and receiving antenna both will be situated on the Earth surface, and Earth surface is not a planar surface, rather it is spherical, and therefore the direct path from transmitter to receiver, as we consider from suppose origin to point P, is not always available, especially when the distance between the two antennas, the transmitter and the receiver antenna, is more than the horizon. Okay, horizon beyond which there will be no line of sight path available. Okay, so because of this spherical shape, the line of sight communication will not be possible, and so there will be some different mechanisms which will be used for this propagation, or actually these are not various mechanisms. These are the various mechanisms provided by the nature itself, which are incorporated for making communication in such scenario. The second thing which is, or the second factor which affects this propagation of radio waves or the communication link is the atmosphere itself. As we know that the atmosphere surrounding the Earth extends from the surface of Earth up to a height of 600, approximately 600 kilometers. And there are various layers in this atmosphere, like the one which is closest to the Earth's surface or which is directly surrounding the Earth's surface is the troposphere. Then as we move upward, we find different layers like stratosphere or ionosphere and so on and so on. And all these layers have different electrical parameters with respect to radiation or with respect to with respect to electromagnetic waves of our concern. You have layers having different densities also. You have layers having different conductivity also. You have layers with different permeability also. Even when you are in a particular layer, the quantities are not homogeneous throughout the layer. Okay, the parameters, these conductivity, the density, they can vary with respect to the uh, with different location across even across a particular layer also. So the atmosphere is also a very important factor which affects the uh, wave propagation, and it makes the analysis difficult. The third thing is interaction with object on Earth's surface. When we had considered the communication phenomena or the antenna analysis in, in infinitely free space, we considered that there will be no object in between the transmitter and receiver, the link between transmitter and receiver. And also we considered that there is no other object all around. But in practical scenario, if there is a line of sight path, suppose the receiver is not beyond horizon, rather it is before the horizon. In that case, you are having a line of sight path, but because of other objects in the surrounding, there are many other paths which, due to reflection, refraction, diffraction, scattering, they produce some other, they provide path for different waves from the same source to reach the receiver itself. That means in this particular case, when what I was trying to explain is that in practical scenario, there is not just a single path available between source to receiver, but in many situations, or in generally every situation, there are multiple paths from source to receiver for reaching these particular waves. And such a environment is known as multipath environment, which is very frequently used in cellular mobile communication environment, where the transmitter and receivers are generally in rural area, in urban area, or if and the distance between them is not very large. Okay, so these three are very important factors which affect the radio wave propagation. Okay, so we'll look here interaction of propagating radio waves with surrounding objects and several layers of atmosphere, and try to find occurrence of different phenomena such as reflection, refraction, diffraction, scattering, and all that, and then try to superimpose the results of these phenomena as per our requirement. What does this mean? This means that actually these phenomena, any one or any two or all of them, these phenomena can occur when there is a communication going on between transmitter and receiver. And on the basis of the configuration of the surrounding, we have to choose that which phenomena or which phenomena are involved in the uh, in the radio wave propagation. Okay, so what we do, we will implement several models for different phenomena, and then as per our need, we can incorporate them to get the better results for the field at the receiving end. Okay, so the first mode of propagation we will consider is ground wave propagation. The ground wave propagation is the propagation in the layer, in the first layer of the atmosphere surrounding the Earth's surface. That means the troposphere itself. So this propagation will be in between the two, in between the Earth's surface and the troposphere. This will be in between the troposphere itself. As we know, the troposphere is the lowest layer surrounding the Earth's surface, and when there are many communication phenomena go on in between these two, in between this particular layer. As we know that the troposphere is extended from 8 to 15 kilometers from the Earth's surface. So this phenomena or this wave propagation is known as ground wave propagation. So here you can see in figure 43 the multipath environment, as I had already explained to you. In this multipath environment, you can see that there is an Earth surface. This horizontal line here is the Earth surface, and on the Earth surface you are having a transmitting antenna. This transmitting antenna can be like your mobile phones, and there is a receiving antenna. For this particular case, we consider that this receiving antenna is the base station antenna. Generally, base station antennas are quite high as compared to the transmitting antenna. That's why I'm saying. Otherwise, it can be a police wireless system in which you are having uh, direct communication. Okay, so this is the base station in our case. So it is a transmitting antenna, it is a receiving antenna, and this path which is through which the waves are directly reaching the receiving antenna from the transmitter is known as the direct wave or direct path. But due to surrounding, there can be several objects. These several objects can be building, they can be forests, they can be trees, they can be cars, they can be even this ground surface also. So all these will provide multiple paths for reaching waves from the transmitter to receiver. As you can see, one of the example, this wave, this red wave you can see. So this red wave is another path other than this direct path through which waves from transmitter to receiver can reach. Okay, this path is in particular case is known as we are expressing it as a reflected path, reflected. There can be many other phenomena, like if any object in between the surrounding is such that that the size of that particular object is very less as compared to the uh, wavelength of the wave propagating. In that case, what you have phenomena is the diffraction, and there may be possibility that because of the variation in the density of medium, you get bending of electromagnetic waves due to from their normal, as we had already known. Then there will be a refracted wave, and there can be different phenomena in between them. That's why for the time being we are considering that there is only reflected wave and this is the direct wave, and jointly this complete environment is known as the multipath environment or multipath propagation environment. uh, the direct wave along with these reflected waves, direct wave itself, which is following the line of sight path. Line of sight path is the path joining the transmitter and receiver through a straight line directly, as you can see in the direct wave. So direct wave, reflected wave, refracted wave, diffracted wave, scattered wave, all these waves jointly known as space waves. Okay, all these waves are jointly known as space waves, and these space waves they are responsible uh, for making transmission in a multipath environment. Okay. Okay. So this is known as the multipath environment as shown in the figure 43. Now we are starting the very first case of wave propagation, in which we are just having a transmitter and a receiver, and the distance between them is capital R, as you can see here, and there is no other object surrounding. This is the ideal environment. This environment or this model is known as free space propagation model. Okay, in this we are considering that there is no surrounding, the surrounding to this transmitter and receiver is completely a free space. There is no object surrounding them, and it is same as the model or as the environment we had been assuming in many of our antenna analysis. Okay, so here we are having a transmitting antenna TX. Here we are having a receiving antenna RS. The distance between them is capital R, and this capital R is very, very large as compared to lambda. We consider this RX to be in the far field of the transmitter itself. Okay, and suppose that transmitter antenna TX is sending some power. Suppose PT, P of capital T is the power transmitted by the antenna, and PR will be the power received at this receiver. Okay, then if you are saying that it is a transmitting antenna PT, and we suppose that gain of this antenna is suppose GT, and we know that what is the meaning of gain of antenna. So gain of antenna is actually it shows the uh, amount of power effectively radiated through this transmitting antenna. So if PT is the transmitted total power, transmitted power, and GT is the gain, in that case PT into GT will be the power radiated by this antenna. So what amount of power this antenna is radiating? It is radiating PT into GT, and the unit is watt. So PT GT watt will be the power radiated by this antenna in free space. Now, as we are considering that the free space surrounding this communication model is free space, there are no other obstacle, and we are also considering that R is very, very greater than lambda. So as long as the wave travels more and more distance, their wavefront become more and more spherical. Okay, and that is why when PTGT power transmitted by this antenna reaches up to the receiver RX after traveling a distance capital R, the power density at that particular point, power density at the receiving antenna will be given by PTGT upon 4 pi R square. Actually, this is the actual result. This is the result PT upon 4 pi R square when you are considering the antenna to be of perfect. Okay, the gain of the antenna is 100%. It is 1 GT. But when generally GT is not 1, it is somewhat less than 1. That's why the uh, power density at the receiving antenna is given by PTGT upon 4 pi square. It is very obvious. Okay, when you are considering the distance between transmitter and receiver to be capital R, in that case you can consider the transmitting antenna to be situated on the center of a sphere of radius capital R, and the receiver is on at the surface of this sphere. And when this transmitting antenna is radiating, it is radiating isotropically. That means it is radiating in all possible direction, and that's why as power reaches the surface of the sphere, the power density, power per unit area at any point will be given by PTGT upon 4 pi square, where PTGT is the total radiated power by the antenna. Okay. So this is the this PTGT upon 4 pi r square is the uh, power density at the receiving antenna. If we are considering that GR is the gain of receiving antenna again. So if GR is the gain of the receiving antenna, and we consider that AR is the aperture of the antenna, receiving antenna, then aperture of the antenna and gain of the antenna are related by AR is equals to GR into lambda square upon 4 pi. Now what is aperture? So aperture is an effective area which is capturing the received power density. As we had considered that PTGT upon 4 pi r square is the power density at any particular point or at the receiving antenna. Now, if receiving antenna is having an effective aperture AR, that means this AR will accept the power. Okay. So, since unit area is accepting the power PTGT upon 4 pi r square, the total power accepted by the antenna will be given by PTGT upon 4 pi r square into AR, as you can see here. That will be the total power, and we are replacing this AR by GR lambda square upon 4 pi. Jointly, this expression is written as PR is equals to PT GT GR into lambda upon 4 pi r whole square in watts, of course. This expression is known as Friis transmission equation. Okay, this expression is known as Friis transmission equation, and in engineering, at least in undergraduate course, we perform many experiments with respect to we perform many numerical with respect to this particular expression. Even when you perform some research related to wireless communication or any sort of wireless communication, like suppose you are performing research in wireless sensor network, in that case, many of the time you consider this model or this Friis transmission equation as the I should say the equation used for finding the received power at the receiving end in very ideal environment. Okay, this is the ideal environment. So you can consider it to be used for finding the, I think, the highest or lowest values, as it depends on your application. Okay, so this value lambda upon 4 pi r square is known as free space path loss, and as you can see, this is the function of capital. You are transmitting a particular wavelength, lambda is constant. As distance increases between transmitter and receiver, the received power reduces, and it's a practical thing. And this is very practical to us, that if we go away uh, uh, from the, what we say, the if mobile antenna goes away from the base station, in that case R increases between them, and that's why the power received by your mobile phone reduces, and you say that you are moving out of the coverage area. Okay, so this is the same thing. Okay, now the second model we are considering here is the ground reflection. This model is comparatively more practical than the prior free space propagation model, where we do not consider anything. In general, when we talk about communication, uh, we have a transmitting and receiving antenna, and if nothing else is there, at least we have the ground surface itself. So this is the second model where we are considering a ground surface, as you can see in the figure, this figure 45. Okay, so in the figure 45, you are having a ground surface here. This is the ground surface, and this we consider this to be parallel to y-axis. As you can see, this is y-axis, and this is the z-axis here. Okay, and along the z-axis, we substitute an infinitesimal dipole antenna here. This is the infinitesimal dipole antenna, Hertzian dipole at point P. The point P is at height ht of this ground surface, and the observation point or the receiving antenna is placed at point Q, which is at a height hr from the ground surface. As you can see, obviously there is at least one direct path from P to Q. We are considering the ground to be flat, and the distance between them to be capital D. The distance between transmitter and receiving antenna is small d. So there is a direct path between point P to Q. The distance between this path is given by R1. Okay, and the waves traveling from P, or waves incidenting from P to the ground surface, will reflect from this particular point towards Q. So this is another path. This path is the reflected path. And as we had studied in theory of images, this path following the reflected ray, if you extrapolate this reflected ray, you find that this ground surface can be removed, and you can introduce image of the source placed at point P here at point P dash, just ht depth below the ground surface, and jointly P and P dash, in absence of this ground surface, will produce the same result at point Q as produced by the point P in presence of the ground surface only. Okay, as we had studied in our the theory of images. So now our objective is to find the net field at point Q due to the infinitesimal dipole placed at point P in presence of this ground plane. For making some simplifications, we consider that dipole placed at point P is along x-axis. This is z-axis, this is y-axis, and x-axis is towards yourself in the plane of paper. Okay, this is towards yourself. As you can see, we are representing it by dot, and this dot is towards yourself. Okay, so the antenna is in positive x-axis, and we know that the field, or the electric field radiated by this antenna, when it is oriented, the infinitesimal dipole is oriented along x-axis, the field radiated by itself at any point in far field in YZ plane. This is YZ plane itself. Why I am considering only YZ plane? To make the calculation more simpler. Okay, you can perform the same experiment in any plane, but we are considering it to be YZ plane. This is y-axis, this is z-axis, and axis in front of you. And in YZ plane, we know that theta, the phi angle is 90 degree. Okay, So the phi angle is 90 degree, and corresponding to this phi equals to 90 degree, the electric field radiated by the infinitesimal dipole oriented along x-axis in the far field is given by this particular expression jk eta I0 dl upon 4 pi e to the power minus jk r upon r a phi cap. It is having a single component in phi direction only in yz plane. Keep this thing in mind. Okay, we are making everything clear, and our objective is to just understand how the things are going on. What is this j? J is of course the complex quantity, the square root of -1. What is k? K is the path, phase constant given by 2 pi by lambda. This depends on the, or this gives the phase variation per unit length. Eta is the intrinsic impedance of the medium. We are considering that the medium, the above the ground surface, is just the free space or the vacuum, and we consider it to be eta given by square root of mu 0 upon epsilon 0. I0 is the constant current flowing in the infinitesimal dipole placed at point P. dl is its length. E to the power jkr. What is capital R? So capital R is the distance of point P to point Q. In our example, this distance is R1, and that is why the field reaching to point Q through the direct path is given by this, replacing R1 by R by capital R. Okay, as you can. And the field reaching to point Q due to P dash. You can consider waves reaching from this particular path, or you can consider an incident wave and then reflected. So when wave incidents and reflect back, some of the power get absorbed by the medium below the incident wave, as we consider that this ground wave or the ground is not perfectly conducting material, and that's why it will receive some of the power, or it will absorb some of the power, and because of that we got some sort of reflection coefficient. So we consider that reflection coefficient to be gamma, and that is why the field at point Q due to P dash, if you consider the source at the point P dash, the image, and the field radiated by this will be given by this jk eta I0 dl upon 4 pi e to the power minus jk r2. Why? Because the distance from P to Q is r2. So it is r2 upon r2, and gamma is a quantity which is less than 1. It's a complex quantity. It depends on the conductivity of the medium. It depends on the angle of grazing. What is angle of grazing? So if you look in figure here, I forgot to draw. This is angle of incidence. Angle of incidence is the angle between incidence wave and the normal itself, and the angle between incidence wave and this surface here on which you are considering the normal or surface of reflection. This angle is known as angle of grazing. So you can consider angle of grazing as 90 minus angle of incidence. So this gamma, the reflection coefficient, is a function of angle of grazing as well as the conductivity of the medium and other parameters of the reflecting surface. Even it depends on the polarization of the incident wave also. So it's a complex quantity. For our consideration, we consider it just as a gamma. It's a complex quantity. The resultant field will be the vector sum of the two. Since there are two waves, one is reaching through direct path, one is reaching through reflected path, and both are reaching at particular point P with certain polarization and certain following different path. That's why there will be some vector addition of these electric field, and which will produce the net electric field at point P, which is given by a vector sum of E1 and E2. Since both these waves are having just same component, phi and phi, that's why their vector sum is just normal sum. So this E will be, I think I should write A phi here. I forgot to write A phi cap here. So the net electric field will be given by the sum, and the sum will look like this. Okay, I hope there is nothing. If we consider the point Q to be in very far field, point Q to be very away from the transmitting antenna, in that case R1 and R2 are approximately same, and both of them can be considered approximately equal to D. And if you do not write, they can be considered same. So E will be given by J eta k I0 dl upon 4 pi. This R1 and R2 here, they are same, so we keep them out. And we keep e to the power minus jk r1 as common also. When we find, the result looks like this. Okay, and in the direction a phi cap. Since base are same and we are dividing, power will be subtracted, and the result looks like this. This is equation number 93, and this equation number 93 is the generalized electromagnetic field or electric field at the point Q due to this this ground reflection model. Okay. Okay. Now, if we look in figure 45, what is R1 and what is R2? Let's come to the figure again. Yes. Yeah. You can see. What is R1? This is R1. If we draw perpendicular from point Q to this line, uh, this this z-axis. Okay, when we draw perpendicular, so Q to perpendicular on z-axis will this horizontal distance will be equal to d. And what is this small distance here? This small distance will be ht minus hr. Okay, maybe in the expression. Okay, I'll explain the what is going on. So it is ht minus hr. Okay, so this distance is ht minus hr, which is perpendicular in this particular triangle. This distance is d, and this distance is r1. So r1, using Pythagoras theorem, can be written as r1 will be equal to, or r1 square is equal to d square plus ht minus hr whole square. Uh, because of some, I think by mistake, I have written ht as h1 and hr as h2. Okay, so please consider it as h1 as ht and h2 as hr. So R1 will be given by square root of d square plus h1 minus h2 whole square is equals to this. And this is the, when we keep this d square outside, the expression looks like this, which can be written as like this. Since d is very, very large, we consider this d to be in kilometers many of the time, but h are generally in some meters. And so h1 minus h2 or ht minus hr divided by d will be very, very small as compared to 1. So this expression 1 plus some very small quantity to the power 1 by 2 can be approximated by binomial approximation, which gives 1 plus x to the power n approximately equal to 1 plus nx. So substituting this, we keep this power 1 by 2 here. The expression looks like this, equation 94. And similarly, R2 can be written like approximately d into 1 plus 1 by 2 h1 plus h2 whole square by d. Again, using the same figure and same logic. When we perform R2 minus R1, the result will be 2h1h2 upon d. It is very simple result. And when we have this h2 minus h1, e to the power minus jk r2 minus r1. What is e to the power minus jk r2 minus r1? Or why we think about this? Because this is the quantity here we are seeing here. So e to the power jk r2 minus r1. Yes. E to the power minus of jk r2 minus r1 can be written as cos of k r2 minus r1 minus j sine of k r2 minus r1 using Euler's identity. So, and we have r2 minus r1 as 2h1 h2 upon d. Substituting everything here, the expression looks like this. Again, since we had considered that h1 and h2 both are very, very small as compared to d, this quantity is very small. And this quantity is very small, a very small quantity, very small than 1. When it is multiplied to 2 pi by lambda, it makes this complete angle as very small. And for very small angle, cos of that particular value is very small angle is approximated as 1. Whereas sine of that particular small angle can be approximated at the value of the angle itself. So cos of 2 pi by lambda 2 h1 h2 by d is approximated as 1, and sine of 2 pi by lambda 2 h1 h2 upon d is approximated as 2 pi by lambda times 2 h1 h2 upon d, where h1 is ht and h2 is hr. Keep this thing in mind. So e to the power minus jk r1 can be written as this particular expression. Okay, and using these results above and the equation there, equation number 93, we get this result to be like this. More, it's not general, but it's an approximated. Okay. Now, if the distance between the two antennae is very large, the D is very, very large, and the height of the both H1 and H2 or HT and HR are very small as compared to the land. They are in some meters, suppose 10 meters or 20 meters, and you are talking about 60-kilometer distance. The distance is quite large as compared to the distances, and that's why the angle of incidence is very, very low. When the angle of incidence is very low, and also we consider that the ground is having finite conductivity, which is very small. In that case, we can approximate this reflection coefficient by -1. Okay, so when this condition satisfied, reflection coefficient will be approximately -1. And substituting this -1, gamma is equals to -1 here, we consider that 1 minus 1 is 0, and -1 into this minus become the plus j. Correspondingly, E will be given by this particular expression, simplifying which we get this particular. As we had performed the same experiment or the same analysis many times, when we have electric field intensity, the electric field intensity can be used for finding the power density. The power density is given by 1 by 2 eta times magnitude of electric field intensity square. So we write the same expression here. This is 1 upon 2 eta times mod of electric field intensity square. Substituting the magnitude, when we substitute magnitude, e to the power minus jkd is 1, and the result looks like this particular pattern. This is the power density at the point P. Okay, once we have this power density, we can find the received power simply by multiplying this power density to the aperture of the received antenna. What will be the aperture of the received antenna? So the aperture of the received antenna can be written as gain multiplied by lambda square upon 4 pi. When we substitute it as the received power, we get as this particular expression. And this particular expression, we are having GR, we are having D, we are having H1, H2 as our variable. This remaining quantity can be replaced by PT into GT, the transmitted power, total transmitted power along with gain. So this received power PT, GT, GR into H1, H2 whole square upon D to the power 4. This will be the expression in ground, received power in ground plane or ground reflection model. Whereas in case of the free space model, the expression was like this equation. PTGTGR into lambda upon 4 pi r whole square. Okay, so okay, thank you very much. I think there is some communication problem in between, so please pardon me. Okay, so we will, in our next lecture, we will continue this propagation of radio waves in next part. Okay, thank you very much.